Hi, how are you? My name is Shachar Shemesh. I'm sorry about that. My parents didn't think I'd speak to non-Hebrew speaking audiences. I really don't like usually what I call slide number 2, where the speaker talks about themselves and nobody cares. So I'll just point out that I'm 50. I have programming since I've been 9. Assembly C, C++, D, PHP, Perl, all sorts of languages. I've had programmed for MS-DOS, Windows 95 since 95, Linux, Amiga-DOS, several 8-bit platforms. What I have never did was hardware, up until this came around. So let's back up a little. I mentioned I was 50. As a kid, you know it. Anyone else knows this game? No.
Best thing ever. I don't know this either.
So this is a game I used to play as a kid. It's called Robot Odyssey. It's an escape room game with 5 levels, except the twist here is that in order to escape, you cannot do the riddles yourself. You have to program robots to do the riddles for you. And the way you do that is by putting logic gates into the robots so that they do what you want. It's a game by the Learning Company. It's considered one of the more difficult games of the type. And I used to play it on a computer that's called the Apple II. Like I said, yeah, we have Apple II fans here. Well, why else would you come to this lecture? I mean, come on. Let's be real. It's a contender for the title, the first personal computer or first home computer. And it's of the 3 that have the claim, it's the one that lived as a continuation of that initial model for the longest. But eventually all good things have to come to an end, and it wasn't produced anymore. And now you can't really go to a store and buy one, which you're surprised.
Just your emulator.
Let me get to that in a second. So what happens if you do want to play Robot Odyssey because you realize you didn't finish that 5th level, and you wonder if, as an adult who's had a few more years of experience with logic circuits, you might do better, and you want to play a game this old. So there are options. The first option is Apple II wasn't the only platform this game was programmed for. It also had a DOS version, here viewed with all of its wondrous CGA colors. And that version still runs on DOSEMU. So you can actually run this game on modern hardware. But that's not the only option. You can also use an emulator. This is called a Applewin, which, despite the name, you see here running on Linux using Wine. But recently, it also gained a Qt version in beta. So it even has I guess it's Applewin Lin, I don't know. So that's an option, and it certainly runs the game. Also, it seems like I'm not the only fan of the game. Some kind soul ported the DOS version to a browser game. So you can literally go to robotsodyssey.online and play the game in the browser, including save games, including exporting them to a file so you can move them between browsers. So that's an option. Then if you're really, really, really hardcore, you can go on eBay. Now, the prices here are in Israeli shekels. You should divide by about 3.5 to 4. So around $500 for a working system. You really have to be kind of crazy to do that. So obviously, I didn't do any of that, right? Because seriously, who would do such a thing? Okay, I did all of those things, fine. But I also decided to do the next logical thing, which is implement my own Apple II, right? Raise your hand if, no? Okay, maybe I am the weird one. Now, that sounds like a strange thing to do. Okay, it is a strange thing to do. Sorry about that. The overarching project is called Some Assembly Required. Don't look it up in Google because there's an Australian TV show by that name. The specific project is called CompuSAR, which is computer and the initials for Some Assembly Required. And the only thing that makes any kind of sense is because of something called an FPGA, or Field Programmable Gate Array. Anyone here has any experience with FPGAs? So, about half the people. That's not bad. I'll join in. And in particular, I found a really cheap one on AliExpress that is based on the Spartan 7 FPGA. Spartan is the lowest end series from a company called Xilinx that was later bought by AMD. So those are the cheapest and smallest FPGAs. And this is called the development board. So a company, in this case QMTech, decides to put an FPGA and a bunch of other hardware they think you might want to use on a board and sell it as one piece. Usually they're very expensive development boards, but this one isn't. I'll get to that in a second. So I figured I'll create an Apple II clone. This is not an emulator. This is an actual clone of the computer. But while I'm at it, I'll create other computers that ruled my childhood. And I think this list pretty much can locate you because my list includes the ZX Spectrum. Anyone here heard of the ZX Spectrum? Seen it? Ever seen it? Worked with it? You? Where are you from?
Germany. Germany.
Germany. Europe. Okay? Anyone who grew up in the US ever seen? Okay, well, one. So that computer never really made it to the US. Then again, the next two did, the Atari VCS or Atari 2600, and obviously the king of the 8-bit era, the Commodore 64.
Obviously.
I gave the credit. This is the best-selling 8-bit computer ever. Sold, I think, around 12 million units. So, and then I said, if I manage to, I'll get the computer that I really want, which is the Commodore Amiga, which is a bit of a challenge because it is a more sophisticated computer. And at this point, you may be wondering, how come nobody else did it? And the answer is, they did. Allow me to introduce to you the Mister. The Mister is essentially the exact same thing I described. It's a development board, this time by Intel rather than AMD, sandwiched, I keep hitting the microphone, sandwiched between I/O boards. So these boards don't contain actual compute power, but instead they contain extra RAM or I/O ports they think you might need. And this project has ready cores, FPGA implementations, for any 70s, 80s, early 90s, and some, I think, late 60s computer you can think of, and probably quite a few you can't. So it's a very comprehensive project. And with this project already existing, you have to ask, why would I bother starting from scratch? There is the real answer, but let's put that aside for a second and point this out. I bought the QMTech board for $29.90. A Mister at the time costed $370 for a complete system. So 10 times as much, more than 10 times as much. Now, since then, COVID struck, yeah.
Oh, you said something. Well, I was just curious. I've seen some issues with like counterfeit FPGAs out on the market. I was wondering if you might be concerned about that for paying $2 for.
I have to say that I've seen a lot of references to AliExpress as who buy for China. The only time I really got a counterfeit chip from there, I knew it was probably going to be counterfeit. It was a 6502. I bought two. There were supposed to be original MOS 6502s. I bought two for $3. So I figured there's a good chance, but turned out they were counterfeit in that they were not MOS 6502. They were probably Rockwell 65C. At least one of them was probably Rockwell 65C02, and the other didn't work. And AliExpress refunded the whole $3. So not really. In general, if you buy from AliExpress and the store is called a sequence of letters and numbers, and it was started 3 days before you bought from it, there is a higher chance you get counterfeit stuff. It happened to me again with a more expensive product unrelated to electronics, and again, AliExpress refunded. So not really. The answer is not really. So, like I said, the Mister at the time cost $370. Since then, this is from this week, the price has gone way up and then started to come back down again. The flip side is that not only is the specific QMTech board I'm based on no longer available at all, at any price, but I'm getting the impression that QMTech is liquidizing their stock and shutting down. They're selling several FPGA development boards for less than it would cost you to buy just the FPGA. And they seem to just run out their stock, and it seems like they're trying to go out of business. So that's kind of sad. So just one word about the FPGA. FPGAs, for those of you who are not familiar, implement logic through something called lookup tables. So essentially, instead of actually placing logic gates, you simulate all the possible inputs to the design, either 4 inputs or 6 inputs, depending on the FPGA, and put it in a table all the possible output that those inputs generate, and that's a lookup table. The FPGA on this board, the one I'm using, is the Spartan 7 S15, which has 8,000 LUTs and 16,000 flip-flops and 4 kilobyte of block RAM, which is tiny. It's not even small. It's minuscule, which explains the price, by the way. So the challenge shifted from building an Apple II clone on an FPGA to building an FPGA clone on a cheap FPGA. So at this point, I would like to give you a choice of where you want to focus at, because I have way more material than would fit in an hour. And I think the whole beauty of the open content section is that it is informal. So what do you want to hear about? It's either building a 6502 CPU pretty much from, not pretty much, from scratch, or what it's like to start FPGA programming for someone who's been programming software for 40 years, or building an Apple II, or the design includes a 32-bit component, so I can talk about that. Or I can talk about the YouTube channel I started and what's it like to try and do that. Or I can talk about the Commodore 1541, which I'm doing well, this is a side project, so call it a side project, trying to emulate in software.
Building an Apple II.
Apple II?
FPGA programming. FPGA programming.
Okay, so let's start with the Apple II and do them pretty much in sequence. Okay, no, let's talk about FPGA programming. So let me switch forward for what is a computer. This used to be true, it no longer is. At the time, computers were CPU, memory, and I/O. That's it. We'll get to that. Okay. So the way you program FPGAs is either there are some visual tools where you drag logic gates and create something that looks like schematics of a circuit, but that won't take you very far at all. The main way is through what is called hardware description languages. And so we have VHDL, we have Verilog/System Verilog, which is almost as accurate as saying C/C++. We have various languages that typically don't compile themselves, but rather compile to VHDL or Verilog, such as Spinal HDL. And Xilinx recently introduced a tool that allows you to program an FPGA in C++, which may lead you to think that C++ is the odd one out here, but because that's a software programming language, and that's not true. They all are software programming languages, every last one of them. Even VHDL and Verilog started their lives and still have the constructs to do so as software tools for simulating hardware. And then someone figured that, well, if you can describe hardware in VHDL, why not synthesize this and turn that into actual hardware? And what this means for VHDL and Verilog, but also for any tool that is used for generating FPGA images or hardware at large, is that the programming language provides you capabilities that you can't use. That was a dramatic point in time to do that. So Verilog has loops, but hardware has no concept of loops. The wire is there. What do you mean, do it again? It's there. So the first shock or the first adaptation I had to do was to understand that, yes, the language has functions. They are not functions in the term, the way that I think of them as a software programmer. The second thing to understand, and that actually turned out to be kind of a good thing, what you can notice if you're used to software projects, that if your code is in C++, and now you're trying to use a library that is written in Java or in another language, there's interfacing to be done. And for HDL, that's usually kind of seamless. And the reason for that is because the terminology when programming for hardware is already a very strictly defined interface. You have a module. It has inputs and outputs. These are wires carrying bits. And as such, it doesn't matter if the module is written in VHDL and you're using it from System Verilog, because why would it matter? It's just wires going in and out. So, but it does require rethinking the way you think of encapsulation. Encapsulation isn't actions, it's a state machine. And we will get to the Apple II, so I will actually show examples. So even when you talk about developing for FPGA in C++, which, like I said, Xilinx has a tool to do that. Yes, you write in C++, but you're still writing for hardware. And for me, the process was actually guided by the development tools. So I started doing whatever I thought I needed, and then we'll call it compiler, it's synthesizer. The term in synthesize would tell me, no, you can't do that. I say, oh, okay, I won't. And I was sort of directed around the constraints, and every time I hit a constraint, I would go, okay, why can't I do that? Sometimes I understood, and sometimes I just had to look it up. And the other thing that is easy to forget when you program FPGA is that at the end of the day, everything is analog. When we think of digital electronics as state machines and logic gates, but then there are considerations such as how long does it take from the inputs changing until the outputs are correct, and is your clock really longer than that so that you get the correct signal stabilized before the next clock arrives and locks them into the flip-flops? And then there's the beautiful, wonderful concept of what if you have more than one clock in your design? They need to interact. You need enough setup time from one clock domain before locking it in on flip-flops that receive their clock from the other clock domain. Something called cross-domain clock domain crossing. So there are a lot of things to consider. Xilinx are very good at documenting. Very good. Very, very good. There is lots of documentation. Hundreds of pages of documentation. And they're encryptic. Document 497. Oh, yeah, that's the clock domains document, of course. And people talk to each other by document numbers. So it was a bit of a shock, but getting things working was a huge, The first, everyone here programmed program FPGA. What was your first model you wrote? The very first one. Raise your hand if it was a UART. No? Okay. Okay, let's talk about building an Apple II. So an Apple II is, in my case, it's a 6502 connected to RAM, right? And we need ROM. We need 12K of ROM and 4Ks of RAM. You know why 4K? But I exhausted the asynchronous memory the FPGA has. The ROM occupies 12K, and with RAM, I got to 4K, which is, to be fair, as much as the original Apple II had. So that's fine. And then you hook them together, you give them a clock, and you run them in the FPGA simulator. And you get this, and you're all excited. Right? No one's clapping. Okay. Yeah, no pity claps, please. I get it. It's a bit overwhelming. I'll point you to the specific areas that are of interest. So, you see here, the read-write line is low, which means this is a write cycle. The address is 494 in hex, and the address we're writing is a 0. Okay. The 400 page, 400 to 800 addresses on the Apple II are the text page. So that's where the text that gets displayed is stored. A0 means a black space. Not inverse, not flashing, just black. What this code is doing, it's erasing the screen in preparation to displaying the logo and starting the boot. So what I was seeing here is my CPU that I wrote running on the Apple II, running the Apple II ROM code, doing the Apple II boot. Then again, I posted that on Twitter, and the reply I got was pretty much like yours, like, huh? So the next step, and that's a computer, but it's not a very useful computer. So the next step was adding I/O. Text display. When I started the project, it was very important to me that the I/Os will be modern devices. So that's why the QMTech board is so good for me. Output is HDMI. I wanted input to be from USB. And I want so output HDMI, input USB, and I want the floppy to be on SD card. So the thing is, HDMI is a really tough protocol to implement, so I said, let's hold that off. Let's do the text display through UART. Also, let's do the keyboard input through UART. And we have a reset button on the, we have a button on the FPGA we can route to reset. So let's see how that works. This is the project. And so what I need to do is I need to open a terminal. Let's see. I'll open a new terminal. And we'll increase the font size so that you can actually see something. Now, I've got the FPGA UART hooked up to the computer, so I can run a terminal. That's dev tty USB 0, and I'm running at, I need to transfer 40 characters over 24 lines, 40 columns, 24 lines, 60 times a second. So I'm running at 1 million baud. Now, technically, the UART on the board is supplied by the CP2102, which doesn't reach 1 million baud. It caps off at 961,000 something baud. But strangely, it works. Now, it kind of makes sense that the UART side works because UART has a lot of leniency in hitting the exact baud rate. But the side that connects to my Linux, the CP2102, on one end it has UART lines, and on the other it has USB. So my computer is talking directly to the USB side of the chip, and it asks for 1 million baud, and the chip says fine, despite the fact that the datasheet says it doesn't support whatever. Okay, and now I go here to the hardware manager. No, that's not it. Go to the hardware manager, and I ask to speak to the JTAG. It's this box that talks to the system. And now I go, okay, program the device. And I saved the images I wanted. So I want, of course it doesn't work. Just a second. Okay. So we've got this, and we've got this. We can load this image. Now, obviously, it simultaneously worked really well and didn't work well at all. That's because the Apple II text page is not consecutive. So when the first line ends, it doesn't immediately start at the next line. That's why we have the Apple II logo here, and the prompt, which is supposed to be 2 lines below it, actually here. So I fixed that. I said, okay, let's create an image that scans the correct order. And by the way, these @ symbols indicate an area that is outside the displayed memory. So there are 8 bytes at the end of the page that are never displayed. And now, why did it not remember? Oh, never mind. So fix that. And we have the correct image. By the way, did you notice the @ symbols flashing? When the design is initialized, the memory is zeroed out. And zeroed out are those @ symbols. So you saw them flashing, and then the code would start going and erasing the screen and displaying the logo. So that actually happens on a real computer. You could actually see that on a real computer. But there's supposed to be a cursor here, and it doesn't show. The reason it doesn't show is because the cursor for the Apple II and Apple II Plus, that was changed later, but for the Apple II and Apple II Plus is just a flashing space. Now, that needs some work, right? Because let's start with inverse. So let's see the next step in the process. No, not that one. Okay, it's not flashing, but it is inverse video. Now, let's think about what needs to happen for that to take place, okay? If that was code, it was simple, right? You hit a character. That character needs to be inverse. So you send the escape sequence that serial terminals know to interpret as inverse video. And then you send the character, and then you send the escape sequence that says, go back to normal. But this isn't software. So what we have here instead is a state machine. We get a new cycle arrives, and then we need to ask, have we finished sending the previous character yet? We're running at 1 megahertz. The UART is running at 1 megahertz, but the UART needs 10 cycles to send a single byte, so it will take a while. And then we ask, okay, where are we in the buffer? And we fetch the character and it says what color it is, inverse or regular. And then if it's not the same color as our current state, we need to say, okay, so we need to begin sending the escape sequence. So we need a state machine inside the state machine saying, okay, how much of the escape sequence have we sent? So the idea here is that think about it, you're writing logic pretty much like you would in a programming language, but that logic only covers the current cycle. You can say, I want that to be stored for the variables for the next cycle, and you can say that's what I want on the outputs, but you cannot do anything more sophisticated than that. So the code here actually remembers if it's in inverse or not, and flips that, sends the escape sequence, the proper escape sequences accordingly. What about flashing? Flashing is a matter of counting frames. So we have a character, and the character says, I'm flashing. So we say, okay, how many frames are we? Which frame are we? We are, every 8 frames will switch state. If we're in the first 8 frames, we'll call that inverse. If we're in the second set of 8 frames, we'll call that normal. And that looks like this. Now, at this point, we want some input. So in order to do input, we need 2 things. First of all, we need the input to arrive at our design. And for that, we use the UART receiver. And we also need a way to signal the Apple hardware that we've got a new character. So the way the Apple does it is they have a soft switch. So they have an address in memory, C000. And when they read that address, the answer is the ASCII code of the last pressed key. But there's a trick here, because otherwise we couldn't type the same character twice. So the 7th bit is set if this is a new key. So we read C0000, and then if we got a new key, we read C010. Reading C010 tells the hardware that, okay, we've seen that key, and if we read C000 again, it will give us the same character, but with the 7th bits clear. And the next time we read C000 and read 7th bit set, we know it's a new character. So we need to implement that in the I/O logic for our Apple II. And if we do, let me just do one small change here. Let me switch the font to much better. Okay, I got more than. I need to resize the window to 40 on 24, and this way I get the original proportions. So 40 on 24. Okay. And this way, I can now talk to BASIC. And this is a running BASIC, Applesoft BASIC. I can also drop down to what is called the Apple Monitor. And here I can manipulate the memory directly. But remember, I only have 4 kilobytes of RAM. But what I can do is I can demonstrate the memory layout of the Apple II text area. So if I write 0 to address 400, we see that inverse video @ symbol appears on the left corner. And then if I go 401 and I write zeros, they go sequential up to 427, which is the further right point. But then if I write to 428, I get a third of the screen down. One line down is 480. Does anybody know why?
NTSC?
No. There's a lot of NTSC stuff in Apple II. This isn't one of them. Okay. The reason this is the way is because Steve Wozniak was a genius. Probably still is. I don't know. The Apple II was using a DRAM, and DRAM needs refresh, which means that every so much time, you have to access each of the banks. The DRAM had 8 banks, and you had to access each and every one of them. So what happens here are actually 2 things. First of all, the 6502 runs at 1 megahertz, but it takes half a cycle to set up the address from which it wants to read, and then the other half, the memory has to fetch that address. So in order to work with a 1 megahertz 6502, the memory has to support 2 megahertz. So Woz said, let's use the other half of the cycle to do the memory, to do the display. So the display fetches the information from the memory on the off cycle for the 6502. So there's this multiplexer. It gives the address from the display circuitry for half a cycle, and then from the CPU from the other half. The other thing it does is the display fetching the memory also refreshes the memory. But to do that, we need to access the separate banks repeatedly and consistently. So what Woz did is the first line is on the first bank, the second line is on the second bank, the third line is on the third bank, and by the time we finished 8 lines, we've refreshed the memory and we need to start over. So the next line goes back to the first bank, which is the 428. We saw it on the third of the screen. So he actually integrated the memory refresh with the display. Of course, as a programmer, you curse his... it's horrible. But it made the computer cheaper. Okay. So that's that. We have 15 minutes. Let's talk about the 32-bit aspect. Let's start with why would I even need a 32-bit CPU there? I mean, what you saw just now didn't have a 32-bit CPU. It had just the Apple. There's a lot of things I can do without 32-bit, but there's one thing I really, I can, but it makes no sense, okay? I said I want to read from an SD card. I want the output to go to HDMI. I want the input to come from USB. And I want the files to come from an SD card. Now, an Apple II floppy is 140 kilobytes. An SD card is usually bigger. I don't want to commit too hard. I know there are some cheap ones from I don't know where. But usually it has more. It has room for at least 4 or 5 floppies. Which means that you need it formatted for a file system. So, and the thing is, so there are projects like the 8-bit guys, Commander X16, where they say, fine, we'll write a fat file system in 6502. It works for them because they're the computer. They define what the computer does. But I can't define what the computer does. The computer is an Apple II. And remarkably, the Apple II ROM doesn't include code to understand a fat file system on an SD card. An omission, I have no idea how it came. So I need another CPU there, doing what I want. And if I need another CPU, I might as well have a 32-bit CPU and have an easier compiling experience, with all due respect to Jason Turner, who is compiling C++ or used to compile C++ to 6502. It's still easier if you use a RISC machine. So this is the architecture. On the left, we have the 8-bit side of things. So we have the 6502 and an I/O manager. And on the right, we have the 32-bit side of things. One of the things I decided to do was to use the DDR memory that was on the board. Now, it makes a lot of sense financially because this board has a 256 megabyte RAM, which costs, anyone, DDR3? Anyone wants to wager a guess how much it costs? $20. $3. The chip costs $3. So that's a really tempting thing to do. Problem is, a DDR controller is humongous. Xilinx, the Vivado machine, has a DDR controller bundled with it, written by Micron. It's called the MIG, Memory Interface Generator. And generating for the Micron chip on the board resulted in a core that was 4,500 LUTs. As a reminder, the whole FPGA is 8,000. So a little over half the FPGA just to get the DDR controller. If I disable the AXI bus, AXI is a standard bus for communicating between hardware devices, it gets a little smaller, it gets to 3,500 LUTs, so a little under half the FPGA. With the added benefit of I never managed to get it to work. Some might say it is a disadvantage, I don't know. I did find another core on GitHub that was around 1,200 LUTs. Didn't manage to get that one to work either. So I wrote one from scratch. It took me over 3 months. It was not a pleasant experience. However, it's only 300 LUTs. And I think the main reason why, beside it being brain dead stupid, it's the slowest DDR controller you can think of. Part of the reason is because those other cores initialize the DDR. And initializing the DDR requires powering it on, waiting. And then taking it out of reset, waiting. And then sending it a command to sort of self-synchronize based on temperature and wait for it to complete. And then start sending commands to initialize certain registers And only then you can start using it. It's a huge state machine, which obviously takes a lot of room. And I said, wait, but I have a machine in the design that knows how to do this already. Can you spot it? It's on the top right over there. It's marked in orange. I have a CPU. I don't need to design hardware that will initialize the DDR following this huge state machine. I can write software to do that. And that really downsized the size of the DDR controller. So what we have here, on the 32-bit side, we have a CPU. The CPU has two buses, one for data, one for instruction. The data bus goes to something called an interconnect, which routes the request to whatever device needs to satisfy it based on the address we request. So we have a UART controller, a GPIO controller, a timer and interrupt controller, SD card, USB, HDMI, SPI. It's another simple protocol that is used to communicate with the small flash devices. And all that connects to a cache that connects a multi-port cache, obviously, that can accept several requests and prioritize them, that connects to the DDR controller. And on the 8-bit side, we have a 6502 that essentially talks to the I/O manager and to the cache. Where's the ROM? The ROM is in memory. We already have 256 megabytes of memory. We load the 32-bit loader, loads the Apple II ROMs into memory where the Apple II can see them. The I/O manager is a gateway between the 8-bit world and the 32-bit world. And so when the 6502 asks for an I/O request, the RISC-V gets an interrupt and can satisfy it. This way, a lot of what would usually be hardware happens in software. This is running at 1 megahertz. This is running at 50 megahertz. Now, this design isn't ready completely yet. The modules painted in gray are not yet written. And the modules painted in orange are modules I didn't write myself from scratch. So essentially, most of the design is mine. I have 5 minutes. Do you want to focus on anything? Do you want to ask? Go ahead.
I have a question.
Yeah.
So you were describing the state machine that does the character blinking and the output of the display. Is that part of this design, or is that like something you did initially?
No, that's something I did initially. At the end of the day, this design will have an HDMI output, which I am worried about, I have to tell you. Because here's the thing. The DDR works at 300 megahertz. Why? Because it's the slowest speed that the chip supports, and it's way beyond the speed that the FPGA comfortably supports. So I can't really run it any faster than that. Even as is, I need a cross-domain, clock domain crossing between the cache and the DDR, or inside the cache more specifically. So if there is a cache miss, I need for the cache to hold on whoever did the request, go to the DDR, fetch the data, and then satisfy the request. Now, for most of these, that's not a problem. The 6502 works at 1 megahertz, so even if I do a cache miss, I probably can satisfy it before it notices that I haven't answered yet. The SPI works at 50 megahertz, but it provides its own clock, so if it needs to halt, it can just halt. And the USB, I'm going to use what is called full speed USB, which is 12 megahertz. It's a bit confusing, but 12 megahertz, it's double data rate, which is what DDR means. So it's 24 million bits per second. So divide by 8, it's like 4 megabytes per second. So I think we'll be okay. The SD card is pretty much like the SPI. It's self-synchronous. But the HDMI has to get the data in time. Because there's what is called a pixel clock. And every pixel clock, which is, I don't remember, for 640 on 480 standard VGA resolution, it's something like 15 megahertz, maybe more. And each one of those is a full byte, at least. So it needs to be on time. So that's one module I'm worried about. The other thing I'm worried about is that these are out of production. So I'm not sure. I may switch to another FPGA, or I don't know. More questions?
What would you recommend if one wants to learn programming FPGAs, like roughly?
Oh, that's easy. Find something you're passionate about. The road is hard and frustrating. Find something you really want to achieve. Don't do this sample project because it doesn't teach you anything really. It does teach you, but I like to jump off the deep end. My very first project after doing a UART was writing the 6502. The first iteration. I've since done 3, and I'm probably going to do a 4th one. So I like it. A lot of people find it too frustrating and give up. Okay, one more point. All of this I've described is only half the story. The other half of the story is I started a YouTube channel following the project. Now, turns out that's another project. So, like, I'm running 2 projects in parallel here. There are nice things about it, though. First of all, skills I learned about video editing, about what interests people. And then there's the occasional people who decide to support me on Patreon. 8 people, to be precise, so far, which gives me a total of $29 a month. But it's nice that I'm able to buy hardware from Patreon supporters, and I think anyone who puts their money there is a huge thing. And of course, everything is open source. Everything. Now, which leads us to one final question. So, does it run Robots Odyssey? No. We need to write. I need to finish writing an operating system for the 32-bit side. I need to get HDMI working. I need to get USB working, which will require creating a new daughter board because the board doesn't have USB. But I think the fun is in the road. Thank you.
Z80 would be your next point line. Z80 would you emulate do an FPGA for the Z80 CPU to emulate to one CPU CPM?
I'm sorry, I didn't understand.
You don't know that the Z80 CPU used to run 8-bit CPM. Another popular
the Z80.
Yeah.
The ZX Spectrum runs on Z80. I think once the infrastructure is there, everything else will be simpler, but it's not on my immediate plan right now.
Okay, I'm just curious.
But there are plenty of open source projects available for all of those.
Yeah, but
Would be for your HDMI, you're saying 640 by 480. Have you thought about just doing 320 by 240, running it, you know, changing the data at half the rate?
The 320 isn't high enough resolution to display Apple II high resolution page. I know many people think it is, but are you familiar with Apple II double high res?
No, I just quick Googled it and it's at 280 by.
Right. That's every pixel displayed in that mode is actually 2 pixels, and they can actually be shifted by half what they would call half a pixel. So that's not effectively the real resolution.
Okay.
tricky.
Yeah, there's a basic command to go into HDR mode.
HDR is 280 on.
Oh.
But like I said, it's not really 208.
Oh.
So thank you.